All right, we're here on Thursday, the 25th of February. We're starting the second chapter of Unit 2, which is Chapter 23, the electric fields. We did a little bit of work with electric fields at the end of Chapter 22, and we'll just review real quickly. Then we're going to discuss the electric field of a point charge, which we briefly studied at the end of chapter 22, the concept of electric field lines, and then we're going to get into electric fields produced by two or more charges, and how to calculate those. So we're in the first two sections of chapter 23. Homework 6 is not going to be due until the 8th of March. Give you a little bit of a break after the exam. And I'll upload that on the morning of the 2nd. So learning objectives, what you should be able to do after covering the unit. It's been a little while, so let's start with a quick review here. If you have Coulomb's law, so if you have two charges and the magnitudes are Q1 and Q2, we can calculate the magnitude of the electrostatic force that they exert on each other. It's the product of their charges, the net charges, divided by the square of the distance between them, and then this constant K, which is called the dielectric constant, or sometimes this is expressed as 1 over 4 pi epsilon naught. They're both the same magnitude. Okay, 1 over 4 pi epsilon naught is K. So it's just the constant in front of these charges in the square of the distance. So these are the magnitudes of the charges, and then the direction of the electric field is along the line joining the charges, and it's either repulsive if they're the same sign, or it's attractive if they're the opposite signs. So that was Coulomb's law. Then we got into a little bit of the electric field. So in practical situations, it's a lot easier to work with electric fields when describing interactions between charges than it is to deal with forces. One of the reasons electric fields can be measured. So when you get into phenomena that including like cell membranes, laser physics, wireless communication, and several other areas, this concept of the electric field is very important. So in this chapter, we're going to go over how to calculate the electric field for some simple situations that provide a reasonable approximation to many practical problems. Then once we are able to calculate the field, we will get into the concepts of potential difference in the coming chapters, or what some of us know as voltage, and then we'll be getting into electronics. So in reality, most practical problems you can't calculate. It's too difficult to calculate the electric field, but there are some simple situations that we will model and we'll be able to calculate it. And these models become a fairly good approximation for many practical situations. So to calculate the electric field, remember we placed this positive probe charge Q0 at a given point, and we calculated the net force using Coulomb's law. Due to each of the source charges, we calculated the net force on that charge Q0, added up all the vectors to get the total force acting on this probe charge Q0, and then at the end, we divided out this force by Q0 to get the electric field. Okay. And so this force is in units of newtons per coulomb. So in other words, the electric field is the magnitude of how many newtons of force is exerted for each coulomb of charge placed at that point. And so once we know the electric field at all of space, we can calculate the force on any charge placed there just by multiplying the charge by the field. And so in practice, it's much easier to work with electric fields than to have to calculate Coulomb forces due to each pair of charges. That's just not very tractable. So here are some magnitudes just to show of the magnitudes of the electric field. So inside a current carrying wire, the electric field strength is relatively small. It's about on the order of 10 to the negative 3 to 10 to the negative 1 newtons per coulomb. Stronger near the Earth's surface. When you rub objects together, you can get strong fields, and an even stronger field on the order of about 3 million newtons per coulomb is required to ionize air and cause arcing in air. So you need a strong electric field to rip charge off of the air molecules. And then inside the atom, you have very strong electric fields which hold the electrons. They basically form the glue that hold the electrons inside the atom. They bind them to the nucleus. So we're going to study a few simple models where we know the answer to. We're going to develop expressions for the electric field of a point charge. We already did. The electric field of a line of charge, which will be simulating a current carrying wire. The electric field of a plane of charge, which will simulate a component called a capacitor, which we deal with in electronics, and the electric field of a sphere of charge. So we're going to be looking at these four cases, more so this first one today. So these four can be used to model many realistic charge distributions in chemistry, physics, and engineering. So let's go through again and calculate the electric field of a single point charge. Okay, so we have this positive charge here, Q, and we'll put the origin at Q, and to find the electric field at every point, we have to take this positive probe charge Q0. And at each point, we're going to place Q0, and the force that Q exerts on Q0 can be calculated by Coulomb's law. And if Q0 is the probe charge and Q is the source charge, then the force is KQQ0 over R squared, where that's the distance. And then we divide through this force by Q0, and we get the electric field produced by a single point charge. So why do the field lines point away from the positive charge? If you have a positive source charge, why do the electric field lines at every point away from it? Well, the answer is, remember, these field lines are show the direction of the force on a positive probe. And so if we place our positive probe charge Q0 anywhere, it will be repelled by Q0, and so the force will always point outward, okay, because the positive probe is repelled by the positive charge. Now you go over here and you can have a negative charge Q0, that's the same sign, okay, and that will have the same magnitude of the field because it's the same magnitude Q. So when you plug it in, you get E is KQ Q0 over R squared, and then divide by Q0. But in this case, the field lines point toward the negative charge. And that's because, remember, the field lines are in the direction of the force exerted on a positive test probe. And the positive probe charge placed anywhere will be attracted to the negative source charge. So this illustrates one important example, is that field lines always go away from positive charges because the probe charge will always be repelled, and field lines produced by negative charges, the field lines will always go toward the negative charge. So in this case, you should be able to calculate the electric field due to a positive or a negative source charge. It's just KQ over R square. And then for a positive charge, the field lines point away from the charge, and for a negative probe charge, for a negative source charge, they point toward the charge. Okay. Another main thing is that the electric field of a point charge goes as 1 over R square. Okay. So every time I double the distance from the source charge, the electric field strength decreases by a factor of 4. Okay. So it gets weak pretty fast as you move away from the charge. Now, in principle, we could describe the electric field due to a charge by drawing vectors at every point in space, okay, where the magnitude of the vector at a given point is proportional to the magnitude of the electric field strength, and where the direction gives the field's direction, okay. And so to do that for a positive probe charge, for example, every time you double the distance away from the positive charge, your length of your electric field vector would decrease by a factor of 4. Okay, so this is one way of obtaining a pictorial description of an electric field, is just to draw vectors at every point in space. Okay, when you start getting into more than 1 or 2 source charges, this becomes a pretty impractical method. It's also impractical to draw vectors at every point in space. And so we're going to introduce this concept of the electric field lines. And these are, you can think of these as lines of force. Okay? And so we draw these lines emanating from the positive source charge, and the strength of the electric field at a given place is proportional to how densely packed these lines are together. And we'll get into some other properties of these field lines, but it's much more practical to deal with electric field lines to visualize the field than it is to draw vectors at every point in space. So we talked about that. So this is just, electric field lines are a graphical method for visualizing the electric field or the effect of source charges on other charges placed in the area. So we calculated the electric field for a single charge. What happens if we have more than one charge? Okay, well, it's easy. In principle, it's easy. Suppose we have 3 source charges. Okay. We would calculate the electric field at a given point due to charge 1 only, and then draw a vector. Then we would calculate the electric field at the same point due to source charge 2 only, and we'd draw that vector. Then we'd calculate the electric field at the same point due to a source charge 3, and we'd draw that vector. And we just add up all the vectors, okay? And this is what's called superposition, okay? If we have many charges, source charges, and we want to calculate the effect of all of them on a probe charge, we just calculate the individual effects due to each source charge, and we add up all the vectors, okay? So this isn't too bad for a couple charges. But again, this gets pretty impractical when you get into realistic situations where you have many source charges. Here's an example of the field lines. So let's suppose that we have 2 positive charges here, Q1 and Q2. And let's just, for simplicity, suppose that they're the same magnitude. Okay, but they're both positive. So this is the resulting electric field. Okay. So what we see here is that all the points on these dotted lines here, the electric field here is 0. Okay. Here it's positive. So let's look at what happens in the middle here. So why is the electric field here in the middle 0? Okay, well, if we put a positive probe charge right at the halfway point between Q1 and Q2, it will be repelled by both of them. So the force that Q2 exerts on this probe would be to the left. The force that Q1 exerts on this probe charge Q0 would be to the right. And the vectors would be the same length because they're the same distance from each of these charges to the source charge, and that both charges are the same magnitude. So the electric field here would be 0. Okay, let's go over here to the right of Q2, and let's stick our probe charge over here. Well, it would be repelled by Q2, so that force would be to the right. It would also be repelled by Q1, okay? But the effect of Q2 would be much larger because the probe charge is much closer to Q2 than to Q1. And so the electric field over here looks pretty similar to that of just Q2 alone. Q1 doesn't have as big of an effect, although the field lines are curved a little bit. You can go over to the left of Q1, and again, Q1 will have a much larger influence on a probe charge here than Q2, and so the field lines over here are dominated largely by Q1. What happens if we were to go up here along this y-axis? Okay, well, Q1 would repel this positive probe charge, so the force due to Q1 would be off at some angle here and pointing upward and to the right. The force due to Q2 would be repelling, and that would be along this line to the left. And since the charge along in this line anywhere is equal a distance from Q1 and Q2, these vectors would be equal magnitudes. The horizontal components would cancel, the verticals would add, and the electric field would be along the vertical direction. Okay. We could go down here, and the electric field would point in the horizontal direction. It would be repelled, the probe charge would be repelled by Q2, it would be repelled by Q1, and so the vertical components add in the negative direction, and the horizontals cancel. Okay. So these are the electric field lines produced by two positive charges. The last example that we're going to do today, and the most important one in many respects, is the electric field due to equal positive and negative charges. So you have a positive charge plus Q, a negative charge minus Q, and they're separated by some distance s. In this configuration here, a positive and negative charge separated by some distance s is called an electric dipole. And we'll see that it has many examples in physics, chemistry, and engineering. Polar molecules, antennas, electromagnetic radiation, all described by the electric field of a dipole. So let's take a little bit of time and let's try to solve this problem for the field of a dipole. Okay, so ultimately we're going to calculate what the field is along some axis perpendicular to the dipole, so the x-axis. But first let's start easier. What's the field like along the axis? Okay, so suppose that we stick our little probe charge at the origin. Okay, well, the positive probe charge will be attracted to this negative charge, so that field would be downward. It would be repelled by this positive probe charge Q, so that vector would also be pointing downward, and yet the net electric field would be in the downward direction at the origin, okay? Because it's attracted to the negative, it's repelled by the positive, okay? Now let's stick our little positive probe charge along the axis and somewhere up here, okay? Well, here it's going to be repelled by the positive charge, and it's going to be attracted by the negative charge, but the probe is closer to the positive charge, so that force will be stronger than the attractive force toward the negative charge, and so the net electric field is upward along this axis of the dipole up here. You could go down below the negative charge and we'd see what its positive probe charge is attracted to this negative charge, so that force would be upward. It would be repelled by this positive charge plus Q, so that force would be downward, but the upward force would be greater because the probe is closer to the negative charge. And so here the electric field would be pointing upward as well. So along the direction of a dipole, the force points upward. Okay. Now what about over here? The next thing we want to do is we want to calculate the electric field along an axis perpendicular to the dipole. So what we need to do first is we need to draw the forces on this positive probe due to each of the charges. So we stick our probe charge here. It will be repelled by the positive charge plus Q, and so the electric field due to plus Q is in this direction. The positive probe charge will be attracted to the negative charge down here, and so that electric field due to the negative charge would be in this direction, and the total electric field is obtained by adding the vectors. And you can see in this example that since the positive and negative dipole source charges are the same distance from this axis, that the magnitudes of these fields are the same. Okay? And so the x components will cancel and the y components will add, and the net dipole field will be downward. Okay? So let's actually calculate it for this example here. So we already discussed this. Okay, the y components will cancel because of what's called symmetry. It just means that because this point on axis is the same distance from both source charges, that the y components due to each of them are or the x components. Sorry, this should be the x components cancel, and the y components don't, I'm sorry. The x components cancel because you have two equal and opposite components that cancel each other out. Okay, so what we need to do here is we need to calculate the y component of this electric field. And so if we define this angle here as theta, which means that this angle is theta, we get that the y component is e sine of theta for each of these. So what we have to do is calculate the magnitude of E due to each force, and then we have to calculate this sine of theta. So let's start here. Remember that E is equal to, due to this point charge, is K times the magnitude of Q minus over the distance squared between the probe charge and this negative source charge. And that distance here, if we go back to this picture, is equal to x squared plus 1/2 s squared by Pythagorean's theorem, square root. So that's the distance from the probe charge located at this distance x along the x-axis and the negative charge. The distance between that charge and the positive source charge is the same thing. It's x squared plus s over 2 squared to the 1/2. Okay? And since we now know the distance between each of the source charges and the probe charge, we can get the magnitude of the electric field. Okay, it's just K is equal to K times Q over X squared plus S over 2 squared. Okay, so that gives that term E plus or E minus in here. Okay, now we have to get what the sine and the cosine is. Okay, so in this equation, sine of theta is opposite over hypotenuse, and that is equal to 1/2 s over x squared plus s over 2 squared. Okay. So now we can add up the fields due to the positive and minus source charges of the dipole, and here we have that the x components cancel. Okay, the components in the I hat, or I hat is a unit vector along x. Recall that from 1150. And the minus, the field is in the negative x direction. And then for the y directions, the fields are both in the negative y direction for both of them. So we add these up, and we get that the net electric field, the total electric field, is negative kq, where q is the magnitude of each of these charges. Where am I? S is the distance between them, and then it's divided by x squared plus s over 2 squared to the 3/2 power. And remember, the 3/2, you get x squared plus s over 2 squared, that's equal to the distance squared, and then we get this final x squared over s over 2 squared over 1/2, which is the sine. Okay, so we plug that in. So now we have the equation for the electric field of a dipole. Okay, now in most situations, for example, if this dipole moment, positive and negative charge, if this were two ends of, say, a sodium chloride molecule, where the positive end is closer to sodium and the negative is closer to chlorine, when you're talking molecules, the separation is on the order of 10 to the negative 10 meters. And so in most cases, this distance x, where we're calculating the field, is so much larger than s, the separation between the charges, that in our formula, we can basically neglect s over 2 squared in comparison with x squared. In other words, it's so small compared to x squared that we can basically blow it off. Okay? And when we do that, then the denominator becomes x squared plus 0 squared, which is x squared, to the 3/2 power, and we get that far enough away from the dipole, the electric field goes as 1 over the cube of the distance from the dipole along the x direction. And so this is an approximate expression for the electric field of the dipole if we get much further away from the dipole than the separation between the two charges, which is easy to do in practice. Now, usually what we'll do is there's what's called a dipole moment. Okay, you chemists might have heard of this. We define the dipole moment as equal to the charge q, the magnitude of each of these charges, so it's q times the distance s. So the product of the charge q and the separation s, we call that the dipole moment, and the dipole moment is written as p, and it's a vector. So the dipole moment points from the negative charge toward the positive charge, and its magnitude is equal to q times the distance. Okay, and so we can write qs as the dipole moment p, and we get that the electric field of a dipole goes as negative k p over x cubed. So that's the field of a dipole, which is two charges that are equal and opposite. And And so it's tempting to say that the field here would be zero because you have a positive charge and you have a negative charge, so the net charge on a dipole is zero, but it still gives rise to an electric field. It just decreases relatively fast because it goes as 1 over the cube power of x. So another interesting thing about dipole moments is that if there's multiple dipole moments, to get the total, we add the vectors. Okay, so let's look here. If you have a single negative charge and a single positive charge, and their magnitudes are q, the dipole moment points negative to positive, and its magnitude is q times s. What about a water molecule? Okay. Here's a water molecule, and it has 2 hydrogens and it has an oxygen. Okay, and the oxygen we discussed, I think, a while back. The oxygen part of the atom is a little more negative, and the hydrogen is a little more positive. Okay, and so there's a dipole moment here pointing from negative to positive, or pointing from the oxygen toward the hydrogen. Similarly, with this bond right here, this ionic bond, the electrons aren't shared equally either. Remember, the negative charge tends to be closer to the oxygen, the net positive charge closer to the hydrogen, and so you have another dipole moment pointing from oxygen to hydrogen. And to add up the 2 dipole moments to get the total, their horizontal components cancel, the verticals add, and the net dipole moment for a water molecule points downward away from the oxygen. And so we call water what's called a polar molecule. It has a dipole moment. And one important application is atoms and molecules that have dipole moments can interact with electromagnetic radiation, and they can absorb and emit radiation, infrared usually, or microwave. And that becomes very important in a field called spectroscopy. So that's the definition of a dipole moment. Finally, here's the electric field of a dipole. So if we were to calculate the electric field at all points in space and draw our little vectors, they would look like this. But the electric field lines, by definition, are tangent to the electric field at every point in space. And so here's where we calculated it halfway between the 2 atoms and along an axis perpendicular. Remember, we have the electric field points down. Go over here, it points down. If you go over to the positive side here, it points to the left. Remember, because it's repelled more by the positive charge than it is attracted by the negative. If you go over here, the field points to the left because it's more attracted. The probe charge is more attracted to this negative charge Q than it is repelled by this charge Q, positive Q, so the field points this way. And so you get this electric field of a dipole. So this is once we know the electric field, this is the force per charge that any charge Q would experience anywhere in space due to this dipole. And we see again that the electric field lines always begin on positive charges, and they terminate on negative charges. The number of field lines per area, so the more dense the field lines are, the closer they are together, the stronger the field. Okay, so the field is very strong near either of the source charges, but the field gets pretty weak as we move away from the charges, right? The field lines are further apart. They're not as close together. So the density, the number of field lines, is proportional to the strength of the field. And so we're going to get into electric field lines a little more with other charge configurations. But this is enough for today. So here's what you should be able to do if you go back um, to here. Uh, you should be able to calculate the electric field for either a positive or a negative point charge and sketch the lines. You should be able to calculate the field due to either two positives or a positive and a negative charge, the dipole or two positives. You should be able to calculate the electric field for other problems with only a few charges, like a couple charges at the corner of a square. You should be able to interpret a sketch of electric field lines, and you should be able to define a dipole moment. So that ends today's lecture, and next Tuesday we will continue this chapter. Probably take about 2 to 3 more lectures to finish. So I mean next Monday, sorry. So I'll be posting those notes Sunday or Monday then. So you have a good weekend. Goodbye.